Okay. Oh. Ok, buenas tardes. Vamos a empezar con el seminario. Alexandra, I'm gonna provide the intro in Spanish. So, hoy tenemos a Alexandra May. Alexandra es estudiante del programa de doctorado de la Universidad de Texas en Arlington, del Departamento de Ciencias de la Tierra y Ambientales. Ella tiene un bachillerato en Ciencias de la Tierra o Geociencias de Texas Tech y está trabajando en el tema de serpentinización y los principales parámetros o variables que controlan este tipo de reacciones geoquímicas. Ella tiene un año y un semestre, tiene 3 semestres de estar trabajando en este proyecto y lo que va a presentar hoy es una mezcla de resultados preliminares, una mezcla de una evaluación global que está haciendo de diferentes sitios donde esta reacción ocurre, lo que sabemos de la literatura, y va a presentar las futuras líneas de investigación o rutas que va a tomar para completar su tesis de doctorado. Así que voy a cederle el paso a Alexandra y ella va a presentar su seminario. So, Alexandra, the floor is all yours. Sorry, I did the introduction in Spanish, but you can go ahead now.
Sorry about that. I was not able to hear, but I can hear you now, so I just need to reshare my screen really quick.
All right. We are not seeing your screen yet.
Yeah, I'm sorry. For some reason, my computer. Can you see my screen now?
We can see your screen now.
Okay, perfect. Sorry about that.
It is okay. All right. There you go.
Okay. All right. Well, hello, everyone. My name is Alexandra May, and I'm excited to share with you all today my research regarding the active serpentinization in a tropical monsoonal environment in Costa Rica. So first, I'd like to go over the basics of serpentinization, which is the aqueous alteration of ultramafic rocks forming predominantly serpentine and other secondary minerals such as magnetite and brucite, as well as hydrogen and methane. This process can occur in environments where ultramafic rocks are able to react with water. Some examples are at the mid-oceanic ridges, subduction zones, at the seafloor, and in ophiolites, which are uplifted sections of the oceanic crust that have been thrusted onto the continental crust and are exposed at the surface. Ophiolites are widespread globally and much easier to access than the sites at the seafloor, making them natural laboratories for studying present-day active serpentinization. In ophiolitic settings, rainfall can infiltrate and react with ultramafic rocks in a system open to atmospheric exchange. These processes can generate moderately alkaline fluids rich in magnesium and bicarbonate, known as type 1 fluids. Some of this fluid can either discharge back to the surface or infiltrate deeper into the subsurface and continue to react with ultramafic rocks in a system closed to atmospheric exchange. The higher degree of interactions transforms type 1 fluids into a reduced alkaline fluid enriched in calcium, hydroxide, hydrogen, and methane, known as type 2 fluids. And then finally, these fluids can discharge back to the surfaces as seepages through structures such as faults and fractures. These two photos highlight two key features that are common across serpentinization sites in ophiolitic settings. The first is this yellow-brown precipitate, and then the second is this crust forming at the surface-water interface. These form when the calcium-rich fluids interact with CO2 in the atmosphere, forming calcium carbonate precipitates. So why are we interested in serpentinization? First, these alkaline fluids can provide energy and nutrients to microorganisms that some studies say could be related to the origin and early life on Earth and other planetary bodies such as Mars. Secondly, as many nations look to try to switch to cleaner energy solutions, hydrogen has gained attention. In the energy sector, hydrogen is sometimes referred to as colors that relate to its formation, which is highlighted in this diagram below. Just to give some examples, black and brown hydrogen refer to hydrogen formed from fossil fuels through the process of gasification. This process also produces carbon monoxide and carbon dioxide, so it's considered the less desirable form of hydrogen. Gray hydrogen is produced from natural gas through the process of steam reforming. This process also produces CO2, but if the CO2 is captured and stored, it's referred to as blue hydrogen. Green hydrogen refers to hydrogen produced through the electrolysis of water, producing hydrogen and oxygen molecules. This process doesn't produce any greenhouse gases, but it is expensive and energy intensive. And then finally, white hydrogen refers to hydrogen produced through natural geological processes. Regarding serpentinization, hydrogen is produced through the oxidation of ferrous iron in the reactant minerals to ferric iron in the product minerals. And then finally, orange hydrogen, which is a relatively new term, and it refers to the stimulation of these natural processes. When studying serpentinization, there are still many knowledge gaps, one being the microbial consumption of the hydrogen. Second are the key drivers controlling its production, migration, and accumulation. And then third, if there are any seasonal geochemical, microbial, and hydrological variations. Because hydrogen can be very reactive, we may be able to use methane as a proxy for its production. But when we try to identify the origin of methane, there are still many unknowns, if it's abiotic or biotic origin. Abiotic origin refers to methane produced through physiotroph type reactions. That's where hydrogen reacts with CO2 to produce methane. These processes rely on metal catalysts such as iron, nickel, and ruthenium. Biotic methane is produced through chemosynthetic microorganisms that consume the hydrogen to produce the methane. When we try to identify the origin of the methane, we can run into some issues. One way studies have tried to identify its origin is looking at its isotopic signatures, which is shown in this diagram. This plot is showing methane concentrations versus this carbon-13 signatures across the global sites. We can see that the methane concentrations range from 0 to 500 micromoles. We do see some sites that exhibit higher concentrations. For example, this is our site in Costa Rica. It has the highest reported methane concentrations for a surface manifestation. The two sites that have reported higher concentrations are deeper systems, so a well in Oman, and then this is a borehole in Bosnia. Typically, abiotic methane is associated with enriched signals of carbon-13, and then biotic methane is associated with depleted signatures. So we can see some sites like Oman and Costa Rica have very enriched values, while some sites in Spain, California, and Bosnia have very depleted values. And then other sites have denoted a large potential mixing between the different sources. So when we try to identify its origin, we still are running into some issues with mixing in the signatures. So when we try to understand the hydrogen and methane concentrations and the isotopic alterations, some key variables that are typically overlooked in the literature are looking at the water age structure, meteoric input seasonality, and the consequent transport and mixing of other carbon solutes. So next, I'm going to introduce to you all the global continental serpentinization sites, which are highlighted in this photo. The pink dots are showing sites that have available geochemical and or microbial data in the literature. Some notable sites are the Zimbalist ophiolite in the Philippines and the Samal ophiolite in Oman. I have a photo here of the Ophiolite in Oman. This is one of the alkaline pools. So currently in the literature, there is a lack of a global database of serpentinization studies. And then very briefly, I'd like to highlight two sites, the first in Cuba and then the second in the Dominican Republic, where there have been reports to host serpentinization, but currently there's no geochemical data available in the literature. So next, we're going to look at the climate across the different sites. This plot is showing average monthly precipitation and temperature across the sites, and they are grouped by their Köppen climate classification. And we can see that there are climatic differences. For example, in Costa Rica, the country receives roughly 1,665 millimeters per year of precipitation, receives roughly 30 times more precipitation than Oman, which receives roughly 50 to 300 millimeters per year. So we identified that the sites differ by climate, but do they differ geochemically? We conducted statistical comparison tests across the global alkaline sites to see if there are any significant differences. We identified that the tropical pH is significantly lower than arid, cold, and temperate sites. We also identified that the tropical sites have a more oxidizing condition. We did not identify any significant differences in the magnesium concentrations, and this could be due to a different process dominating its mobilization. The tropical calcium, sodium, and chloride values are significantly lower than the other sites, and this could be due to a higher dilution effect and/or shorter water transit times. The tropical carbonate values are the highest values reported, but they're only significantly different than the arid sites, which is dominated by hydroxide. And then we see high nickel and iron concentrations in the tropical sites. We also conducted a statistical comparison test in the surface waters across the global sites, but unfortunately in the literature, there is a lack of sampling in the surface waters, so that did limit my comparisons. But we did identify that there were no significant differences in the pH levels. The tropical sites had a more reducing condition and higher variability with the oxidation reduction potential values. Again, we see that there are no significant differences in the magnesium concentrations. And then we also see again that the tropical calcium, sodium, and chloride values were significantly lower. So next, we'll focus in on the Santa Elena ophiolite in Costa Rica. It's located on the Northwest Pacific coast. It expands around 250 square kilometers and hosts a minimum of 520 cubic kilometers of rock. During all of our campaigns, we have analyzed 8 watersheds, 3 of which exhibit alkaline manifestations, those being the Murcielago, Dantas, and Minas watersheds. During our campaigns, we have analyzed groundwaters, surface waters, alkaline seepages, as well as conducted streamflow measurements and infiltrations tests. Active serpentinization was identified in 2013 by Dr. Sanchez Murillo and Dr. Gazel. During their campaigns, they identified 2 alkaline seepages in the Murcielago and Dantas watershed. The surface waters were identified to be magnesium bicarbonate type, while the alkaline seepages were identified to have high calcium and hydroxide. The methane concentrations in the alkaline seepages in the Murcielago watersheds had enriched values of carbon-13, while the signatures in the Dantas seepages were depleted. And then finally, microorganisms associated with methanol oxidation, hydrogen oxidation, and methanogenesis were identified. And regarding our present-day sampling, it is aimed at identifying seasonal differences in hydrometric, geochemical, and microbial analysis. And then after completing 2 campaigns, I haven't been able to identify any significant differences in geochemistry from previous to present-day sampling. So we hypothesized that in a tropical monsoonal environment, seasonality and rainfall amounts result in more significant water and rock interactions during the wet season, a geohydrogen and methane-rich dissolved phase during the early baseflow condition that decreases in relation to baseflow recession, and then seasonal microbial diversity. So our research is focused in the Santa Elena ophiolite in Costa Rica. It's also referred to as the CEO. Here are a few photos from our site. So this is showing the surface waters. This photo is showing trapped gas under the crust that I showed y'all in the beginning of the presentation. And then these two photos are showing alkaline manifestations. Today in my presentation, I'll be focusing on water and rock interactions from a hydrological perspective. This diagram is showing the typical distribution of precipitation in Costa Rica with two peak discharge periods. The first in late May to early June, and then the second in October. Our sampling has been focused in the baseflow period. So the first at the onset of the baseflow period in January, and then the second at the end of the baseflow period in May. This diagram is just showing all the watersheds we have analyzed, and I do want to highlight a few of them. So the first is the Rio Seco watershed. It's located on the western side of the peninsula. It has a relatively steep slope, and we have not identified any alkaline seepages, so we use it as a control site. The next two are the Minas and the Dantas watershed. These are steep tributaries in the Pochero Grande watershed. We have identified alkaline seepages in both of these tributaries, and they have experienced a larger degree of erosion, which has allowed for a greater portion of the prudotite to be outcropped. And then finally, the Murcielago watershed. It has a more shallow slope and has a higher degree of vegetation coverage. And again, we have identified alkaline seepages in this watershed. We also calculated the evapotranspiration, and it accounts for approximately 63% of the total annual precipitation, which can impact the water balance by reducing the amount of water available for rainfall and available for runoff and infiltration. So we conducted stream flow measurements in 3 of the watersheds, the first being the Rio Seco watershed, shown here. Again, no alkaline seepages occur. In January, discharge from upstream to downstream remained relatively consistent, and then in May, the catchment had dried out. In watersheds where alkaline manifestations occur, we notice that there's a consistent increase in discharge downstream. So for example, in the Murcielago watershed, in January, discharge downstream increased by 8 times. And then in May, we still see an increase by 1.8 times. And then in the Dantas watershed, from January, it's a relatively shorter segment, so we can only do one measurement. And from January to May, it had decreased by 60 times. So in watersheds where alkaline manifestations occur, we see subsurface storage providing sustained flow through intermittent stream sections that are correlated to alkaline manifestations. We also conducted modified single ring infiltration tests to better understand the hydrology of the soils. And then after calculating infiltration rate, which ranged from 20 to 100 centimeters per hour, it revealed a large potential for steady state infiltration in the soils at the end of the baseflow period. So in other words, at the end of the dry seasons, the soils are ready to intake water. So this plot is showing a dual water isotope plot. I have plotted here surface waters, alkaline seepages, the average of the groundwater, and then local precipitation, plotted along the local and global meteoric water lines. And we can see that our values indicate recent meteoric origin and high connectivity between the rainfall, groundwater, and alkaline manifestations. We also analyzed tritium in our waters, and tritium is a good tracer to use to date young groundwaters. And so our samples are plotted here. across the on top of the typical distribution of tritium in the Central American region. And they are plotting close to near natural levels, indicating recent meteoric origin. So a little bit more about our tritium analysis. In January, our tritium values ranged from 0.09 to 0.85 TU. And then typically the Costa Rica precipitation tritium values range from 0.64 to 1.61 TU. And then the groundwater in the peninsula ranges from 0.12 to 0.42 TU. So we calculated preliminary water aids distributions using rainfall data and tritium levels to predict tritium concentrations in the stream flow. To model the water transit times, we used a gamma distribution that was adjusted for tritium decay. And then the model used a Latin hypercube Monte Carlo sampling to run 100,000 simulations that varied the alpha and the beta parameters. And then we keep the best 327 runs with mean average error below 0.1. So this was this is what we produced from that. So we can see that the transit times range from around 1 to 6, indicating that our waters are younger than 10 years. And then I'd just like to highlight some future work we'll be doing during our next campaign. We will be analyzing radon in our waters. And so just a little refresher, radon is a radioactive noble gas that is found in the environment. It's produced through the natural decay of uranium and thorium into lead, and it has a very short half-life of 3.84 days. So radon is a good tool to try to identify gaining streams. Therefore, we will conduct spatial analysis throughout the watersheds to try to elucidate groundwater to surface water connectivity. Because of its very short half-life, if we see an increase in radon in the surface waters, it could indicate groundwater input. Next, we'll look at our geochemical analysis. So this first plot is showing how alkalinity evolves with pH. We analyzed 4 different water types: surface waters, groundwaters, alkaline seepages, and then aguas calientes, which is a spring that's located right outside the ophiolite, and it's associated to nearby volcanism, so we use it as an end member. And so we can see as pH is increasing, our alkalinity becomes dominated by carbonate and hydroxide. This is just another overview of our geochemical analysis. I just want to highlight a few things from this plot. So we can see that our ORP, there's a clear evolution with pH. So as pH is increasing, our waters are becoming more reducing. And then to highlight our alkaline seepages, they have higher values of calcium, chloride, low magnesium, and then low dissolved inorganic carbon, and then dissolved organic carbon. We also analyze trace elements in our waters, which is shown by this correlation matrix. We can see that there's high concentrations of aluminum throughout all the water types. And then we also see high concentrations of titanium in the alkaline seepages. We see spikes of molybdenum during the May campaign. And then finally, we see a trend of high concentrations of iron throughout all the water types. And when we do see some sinks, and these are all surface waters. And then finally, we conducted a PCA analysis, which is shown here. So we were able to explain 62.5% of the total variation in our data, with the first dimension mainly being explained by trace elements. And then the second dimension is mainly be explained by EC and then major cations and anions. We can see that there are differences based on water type. So this red ellipse is showing our surface waters. We do see one outlier, but this is aguas calientes, so it is expected to be an outlier. And then the blue ellipses is showing our alkaline seepages, and we do see one outlier. So this was a sample in May, And because the system had dried up quite a bit, we had to excavate rocks to take the water sample, so that could have affected the concentrations. And then finally, we'll look at our dissolved gas analysis. So our hydrogen and methane concentrations evolved from higher values in January to lower values in May. This plot is just showing how hydrogen and methane concentrations across the global sites. So we can see that the temperate and tropical sites, which are shown in green and then purple, are methane dominated, while the arid and cold sites, which are shown in blue and red, are hydrogen dominated. So many laboratory experiments have set out to try to identify the key drivers affecting the production of hydrogen and methane. This experiment in particular was a 2020 experiment by Barbier, and he varied temperature and reaction time. And if we plot the surface manifestations on top of that, we can see that they are in the range of over 200 degrees Celsius. And so if we look at Santa Elena in particular, they are in the lower range for hydrogen production, but they are in the higher range for methane production. And a reason for this could be that the serpentinization reactions are occurring at a higher rate in these wetter environments, facilitating rapid and abundant abiotic and biotic methane production. And then just to conclude, our tritium and oxygen 18 values indicate recent meteoric origin and high connectivity between rainfall, groundwater, and alkaline seepages. And then our preliminary water age distribution shows that our water is younger than 10 years. Our system is methane dominated, but remember, all of our samples have analysis have come from the base flow period. So it might be interesting to see how our system behaves during the wet season. And then finally, our hydrogen and methane concentrations decrease with base flow recession. So we do have an upcoming campaign coming up in a couple of weeks in December. So 2 new analysis we'll be adding will be the radon measurements, and then we also will be conducting in situ measurements of methane. And then we will continue with all of our analysis of major cations, anions, trace elements, stable water isotopes, DIC and DOC, and then we will try to increase our discharge measurements and infiltration tests. And that's all I have for you all today, and I'd be happy to answer any questions.
Thank you, Alexandra. Let's open the floor for questions. Let me know if you have any questions. So maybe I can start. Can you elaborate more on the role of iron and other metals as alloys for hydrogen production? Why it is important to measure, let's say, iron and nickel, cobalt, and all other species in terms of hydrogen production?
Yeah, so I didn't really go into much detail on the different ways that methane can be produced. So if we look at how abiotic methane can be produced, can you still see my screen? Yes.
Yes.
Okay. So the methane can be produced through physiotroph type reactions, and these reactions can be supported by these metal catalysts. These catalysts actually decrease the activation energy for these reactions to proceed. So that's why we are interested at looking at these metal catalysts. So the most common ones are iron and nickel, but we also see at low temperatures that ruthenium could be the ideal catalyst. And ruthenium is found in chromites, and chromites are common in ophiolitic settings. So a lot of research has been focused on looking at ruthenium for catalytic abilities.
Let me see. Thank you. Let me see. I have a question here in the chat.
Do you have a possible?
Yeah, the decrease in hydrogen and methane with the presence of base flow. Why they are
Yes.
decreasing?
Yeah, so we think that during the wet season, these reactions are being accelerated. And so we still see at the end, because our sampling was in January, so that was the beginning of the base flow period. So we still see that the reactions are being active. But as we continue through the dry season, we see that these reactions are possibly slowing down. And that's why we see a decrease in methane and hydrogen, is that during the wet season, the serpentinization reactions are happening at a higher rate compared to the dry season.
I hope that answered your question, Selene. And so you're working on the using this code provided by Dr. Christian Birker for tritium,
Mhm.
but you already collected samples for SF6, which is
Mhm.
another tracer for dating younger, groundwaters. Can you comment on how similar or different are the ages that we just obtained from the Utah lab?
Yes, so I have also been using the GS Tracer LMP to analyze the apparent age of the water. And I ran a model with the sites where we have both tritium and SF6. And it said that the water ages was of roughly 7 years, 7 to 8 years. So we're getting similar ages when we look at the tritium and the SF6.
Any and Christian is wondering if you will get the type of dilution effect with higher stream flows during the rainy season. So can you explain us why it's difficult to go to the place in the rainy season, and why there is a huge gap in terms of that,
Mhm.
and if everything is going to be diluted in the rainy season, and you probably won't see the springs or anything like that. Yeah.
Yeah, so there's a couple reasons why sampling during the wet season will be difficult. So the first is obviously trying to get to the sites will be a little bit harder due to increased flow. And then also we would see that dilution effect at the surface, but the reactions could be happening in the subsurface at a faster rate, but we wouldn't be able to see that from the surface springs because of the dilution of the rainfall.
Yeah.
Mhm.
So yeah, just to complement that, we don't really know what is going on in the rainy season, because the access is quite limited,
Mhm.
because this is a national park and it's a UNESCO worldwide heritage place as well. So we have limited access during the rainy season. They don't really want people to be there and getting troubled with peak flows. Um, but what we have found is that you can actually see the bubbling from the bed stream. You can actually see from the stream bed, you can actually see bubbling in some pools. And so we really want to see if there are some sites that are wetter or more active during the rainy season. When we visit the sites in the dry season, you can actually see the patches of serpentinization on the rocks, and you will think that those patches were actually active earlier in the season. So the idea of going in December, and especially after this heavy rainfall event that just happened in Costa Rica 2 weeks ago or 1 week ago, is to actually see to capture that. The other point that is really, really interesting that we just were alert is that these springs are happening also in coastal rifts. So we are going to go to the coast, and at the coast, in some places where you are only where the access is only by boat, you can actually see the springs also discharging potentially alkaline fluids to the sea directly. So that's another thing that we're going to be trying to do. But um, something that Alexandra and we had been discussing, and there is a lot of attention right now in terms of natural hydrogen production, especially the U.S. The U.S. is putting a lot of money, is shipping in a lot of money to understand how these reactions happen, and if people can actually escalate this to a larger production of hydrogen. But something that is really interesting is that if you think about dilution in the tropics, and maybe Alejandra can elaborate on that, if you see chloride, sodium, all of those seems to be quite diluted. But if you keep that same rationale, um, there is no reason to see high nickel and high iron. So something is going on differently in terms of the mobilization of those solutes. I don't know, Alexandra, you want to expand on that?
I think you covered most of it. I did see someone possibly asking another question in the chat, but then it went away. But I don't know.
Sorry.
I just saw typing bubbles, but then they went away. But yeah.
Any other question? Oh, yeah, Christian, go ahead, please.
I think I speak up rather than typing questions into the chat.
Yeah, that's better, yeah.
Alexandra, thanks for the great talk.
Thank you.
It's a smashing topic, and
Thank you.
You covered a lot of ground already with sampling. I know the site. It's hard work going to the Santa Elena Peninsula and doing sampling. I wonder if maybe some relatively simple hydrological modeling would help with some of the sites where you have gaugings done already. The only thing is you would definitely need a couple of points, or at least one, in terms of the chemistry during the rainy season. This would be really, really important. I know it's one of those situations where access is hard and it's just very difficult. But I know if you have a couple more concentrations for the rainy season with the gaugings you already have done, you can definitely think of a relatively simple hydrological model to kind of get those relationships simulated.
Yeah,
this would be something really cool.
Yeah, I think that would be really cool. I think especially once because we do have the December campaign coming up, and then we have hopefully we'll be able to go in March as well. So we'll be able to get a snapshot of like the whole year. So I think that would possibly maybe help with the modeling. I don't know, maybe you know a little bit more than me on that. So
I think you're muted.
Yeah, I think you're muted.
Sorry. Yeah,
no, you're okay.
So the problem with the rainy season is that we only have probably access to Murcielago watershed, which is, let's say, close to the Guajiniquil town. The other sites, inland, far away in the peninsula, are most likely inaccessible during the rainy season. So that's the problem. But the idea is to go there and do more flow measurements and chemistry and isotopes during the rainy season. We have been, spending 10 years in this region, and we haven't really sampled the rainy season because of that, because of limitations and access. But I think it's in our plan, in Alexandra's plans, to get at least one system. But Alexandra, maybe something related with Christians. I mean, we have now really young waters, really young waters, less than 10 years. The system is actually pretty young at the subsurface. But some of those springs are almost zero in tritium. So I was telling you that maybe the system is divided in two big pieces: younger waters really close to the surface, and maybe a deeper system that is coming from deeper circulations. What do you think about that?
Yeah, so when going back to the how we did the water age modeling with the code, what I present today, that was just an average. We don't see any changes when we just input the lower tritium values. So when I ran the code with the 0.09 value, we don't see any change in water age. But when I'm using the USGS tracer LMP, when I run just the alkaline seepages, I get an age around 60 years. So I still need to do a little bit more analysis in that topic to see, but I do think that the alkaline seepages are older than the surface waters because of that difference in the tritium value.
Sorry. And the other fact, Christian, is that the area doesn't have a really deep soil. So when we have been doing these infiltration measurements that are really high, actually, is because the soil layer actually is pretty thin, and we think that the water is just going through the system. Is a system that is quite fractured and is changing all the time. So when serpentinization is happening, you have expansion, and the volume is doing like this. And then when you don't have water, everything contracts, and those fractures are sometimes filled by carbonates, and they will open again when they are saturated with water. So it's a really, really interesting system that can be divided, let's say, 2 or 3 simple layers, I think. But we can take your suggestion in terms of the hydrological modeling. I think might be feasible to do.
There is a question in the chat,
okay,
but I think you might be better to answer it. It's about how we decided where to take the groundwater sampling. We haven't analyzed any groundwater in the sampling I've been a part of. That was all done prior to when I have joined the research. So maybe Ricardo, you could answer that.
Yeah, Lorena. So there are not many wells. In fact, there is only one well inside the park that was drilled in the alluvial aquifer for just providing water to the park rangers. However, outside or in the limit of the ophiolite, there are a lot of boreholes that were or had been drilled by the community just to get water. We know that the water table fluctuates rapidly. We have some water table measurements from a logger that we used to have in the area. But yeah, drilling is actually, let's say that if you have the money, still getting the permissions to drill a well in the national park that has a UNESCO status is quite difficult. And so groundwater in this case has been sampled mainly nearby the ophiolite, in some boreholes from the local community and things like that. So that's our best proxy of groundwater. The rest are, springs and surface waters. Any other comments or questions? Okay, well, we don't have any more. So thank you very much, Alexandra, for sharing your research. Remember, for all of those who participated today, we are trying to build community. The next seminar is going to be in Spanish, I promise. It's going to be a professor from UNAM in Mexico, and it's going to be a totally different topic. We also want to include women, people who are doing postdocs, research scientists, not only faculty members. We really want to open this to we really want to open this opportunity to people at different levels. So we will have our next seminar in January, and I will announce it probably in December. So thank you again for your participation and your time, and we will get together again in 2 months. And thank you, Alexandra, for your great talk.
Thank you.
Bye-bye.